I'm Aki Fujimura, Chairman and CEO of D2S. I tell you, it's a real honor to follow Andy. I worked with him in the CFI days when I was at Cadence. The patience and persistence it took, and the skill and conviction to navigate both technical and human aspects of what it took. I don't think there's any other human that could have done what Andy did. Congratulations to what open access has become, and thank you so much, really. Seed of belief in open database is what Andy talked about. Today's talk is about seed of belief in Curvy design. Connect the dots going forward? That's what Polygon edge-based formats do. And they said not to do that, so we aren't. Before I go into Curvy design, I want to give you a little bit of a background about myself. D2S does GPU acceleration for semiconductor manufacturing. But before I got into manufacturing, I worked on physical design EDA, place and route, and standard cell layouts in particular. I was one of the founders at Tangent and managed the development of Tangate, the first commercial over-the-cell routing place and route system that wasn't based on channel routing, that became Gate Ensemble and Cell 3 Ensemble after we got acquired by Cadence. Inside Cadence, my first time around, Joe Costello asked me to be VP of Central Engineering, where Design Framework 2 was being developed. That's when I had the pleasure of meeting Andy. And after that, Steve Teig, Tom Cromwell, and I came back together to break the Manhattan assumptions we embedded at Tangent with the X architecture while we were at Simplex. And as you can see on the rightmost picture, we have recently been working on curvilinear masks. That's an actual SEM picture of a curvilinear mask. All through, I do have a history of working on design formats. I designed DEF. It was designed to be efficient for Manhattan designs, and we did that explicitly. Did you know that DEF was named that because it's the next letters after A, B, C, A, B, C, D, E, F? It was a proprietary format back then and submitted as a standard much later with Jim Hogan, rest in peace, as the force behind it inside Cadence. I mentioned Design Framework 2 and the CAD Framework Initiative before. I understand very well the trade-off between data structure is half of programming, and particularly true for any innovation, anything new, and the need for interoperability. I think interactivity requires open access, while batch needs exchange formats. I was also on the steering group for the new semi-standard in P49 that added multigons as B-spline and Bezier-based extension to more efficiently represent curvilinear shapes with infinite resolution. The photomask designs are already well along the way to being curvilinear shapes everywhere. So Oasis already has a standard for representing curvy designs, even though its intention is to represent curvy mask designs. 1980s is when over-the-cell place and route got invented. Dracula and DRC came to be fully synchronous design with logic synthesis, scan-based test, timing analysis, and timing assurance became predominant. Verilog and all that came together. SPICE and other rigorous simulation technologies had come before that in the 1970s. Back in 1985, the fastest computing device in the world was the Cray 2, 1.9 gigaflops at $15 million. We have 400 million times the price performance now with 105 teraflops for $2,000 for your workstation. I think it's about time we rethink EDA. What we can afford to do should be really different from what we came up with 40 years ago. I said photomask shapes are already curvilinear, and this is why. Bigger the purple oval on the right plots, the more resilient wafer manufacturing is to manufacturing variation. You can see the curvy mask designs on the bottom there get a lot bigger oval. And that's why mask shapes need to be curvilinear. About 5 years ago, the leading edge mask writing machines changed from being variable shape beam or VSB that it's been for decades to multi-beam, where the mask is written with e-beam square pixels, just like the screen that you're looking at, displayed with pixels. Any shape masks can be written in the same mask write time, and that's what broke the dam on the ability to write curvilinear masks to improve wafer manufacturing. So it makes sense that the E-beam Initiative Luminary Survey that you're looking at here shows the mask community pretty strongly believing that curvy mask shapes will be the way of the future for both EUV and 193i, at least for hotspots. But many people believe that it might be the entire mask in the future. This is the sequence. Multi-beam mask writers enabled curvilinear masks, and curvy masks enabled curvilinear IoT. IoT, or fancy form of OPC, can output curvilinear shapes now, and mask shops can produce those masks. Curvy IoT, in turn, enables curvy design. It's possible for curvy IoT to target curvilinear wafer designs now. And so what that means is full chip curvy designs are now manufacturable. That's just in time, I'd say, right? Lithoscaling, scaling is going, but lithoscaling is almost over, right? Devices are going 3D to account for that. Power and clock is probably going to the backside, right? So even more interconnect limited than now. And interconnect in M2 and up can go up in any direction going forward. And that's really the key enabler for being able to make use of curvilinear design. I think Curvy is going to be the answer. Now look what we have here, right? This is from several years ago. IMEC, the foremost research institution in semiconductor manufacturing, has been publishing on curvilinear designs and potential for curvilinear designs for quite a few years now. They've been focusing on standard cell designs, the intra-cell routing inside of standard cells, and you can see that they have been proposing a bunch of curvilinear ways to make standard cells smaller and perform better, and in particular, reduce the number of vias. Plot from the results that they got from an experiment that they ran a year ago, 2 years ago, something like that, where they tried to lay out some common standard cells, and they're saying that number of vias can be reduced substantially. It turns out that Toshiba also had announced similar results in 2002 using the X architecture. At the time, there was no multi-beam machines, so 45 degrees was all you could do. Um, their results shows a transformation of the standard cell layout, intra-connect layout inside on the left, with green showing metal 2, yellow showing metal 1. Transformed into the picture on the right, substantially reducing the number of metal 2, and therefore the number of vias needed to implement exactly the same logic. So in addition to Toshiba showing the standard cells, the X architecture idea was to take advantage of the diagonal connection being square root of 2 shorter and be able to do metal 2, let's say, and metal 3 in Manhattan, and then metal 4 and metal 5 in the diagonal directions. And number of companies, I think 16 companies have used that and uniformly reported significant gains in performance and power and the number of via reduction and even entire layers being reduced in some cases. You can see the example from ATI up at the top. But even before the X architecture, the idea of doing planar connections to try to save space had been around for a long time. So Diane is a paper here. It's a PhD paper that shows various uses of different types of planar routing. And you can see that there is a particular picture that has a curvilinear shape to it. And of course, at the time, that couldn't be manufactured, but now it can be. Steve Teig, who had been in place and route, as I mentioned, but also for the last more than 10 years had been a main chip designer for AI chips, particularly focused on low power AI chips. Now he is a distinguished engineer at Amazon, one of the very few in the world. Um, he has been studying the curvilinear designs as a chip designer, and he feels that it has substantial benefit. In particular, he notes that via reduction is the key enabler to many, many benefits. He did a bunch of calculations, simulations, and came up with some results. So Steve's calculations show that a simultaneous achievement, right, all of it together is 25% performance, 20 to 25% power, 10% area reduction, and all of that coming from 30 to 45% wire length reduction and 40 to 50% via count reduction. Of course, this is only in the routing layers, interconnect layers, right? And performance per watt, which is something that he cares a lot about as a chip designer, low power AI chip designer, is 50 to 60% performance per watt reduction. That's what he's expecting to be able to get from a full implementation of curvilinear place and route. But he's also saying that individually, the following benefits can be achieved. So if you only cared about performance and you were willing to get less benefits in other things, then you can get as much as 40 to 43% power improvement and performance improvement and so on. So the message for this audience is let's get ahead of the curve. Semi-Oasis P49 is already done. So, let's implement Curvy extensions to OpenAccess and let's implement Curvy extensions to Def and Def also. Thank you for the opportunity to speak today. It's a particular pleasure to talk right after Andy. Bye.